Section 25.3, nuclear reactions. Our three objectives here are to distinguish between nuclear fission and fusion, to explain how a chain reaction is utilized by nuclear reactors, and to compare fission and fusion reactors. So to start, let's look at a nuclear reaction. A nuclear reaction is any process that involves a change in the nucleus of an atom. So what we've seen so far is the transfer of electrons, like in electrical circuits, but that's not changing the nucleus of an atom. So a nuclear reaction does do that. For example, if we combine an alpha particle with a nitrogen nucleus, then the result is an unstable form of fluorine. Well, this unstable form of fluorine has a new nucleus, so a nuclear reaction occurred. But this unstable nucleus disintegrates into two stable isotopes, one of which is oxygen and one is hydrogen. Now we'll talk about fission first. Fission is any nuclear reaction where the nucleus splits into two or more nuclei. Now this usually happens for atomic numbers greater than 58. Okay, that's when we have fission. Atomic numbers greater than 58. So as the nucleus gets bigger, okay, we have more chance for nuclear fission to occur. And we talked about this in the last section with nuclear stability. And when this happens, though, we should note that there's a release of energy. A lot of energy is given off. And sometimes byproducts include particles such as photons, or, like light packets, protons, and neutrons. So let's take a look at an example of this. So let's say we have uranium-235. And it's bombarded by a neutron. Neutron has mass of 1 and no protons, obviously. As a result, what we get is barium 56-140 and krypton 93-36. And we also end up getting actually 3 neutrons. So what we see here is that uranium, a single nucleus, split into 2 or more nuclei. Let's take a look at more of this now, actually, to discuss what a chain reaction is. Next, let's take a look at fusion. Now, fusion is a nuclear reaction where 2 or more nuclei combine together, so it's the opposite of fission. And when you think about this, remember the example when 2 bumpers would fuse together when we looked at momentum problems. If 2 bumpers fused together, they were stuck together as one entity after the reaction, or after the collision. Same thing here, when they fuse together, they stick together. Now, some interesting stuff here is that lighter nuclei have a tendency to combine into heavier ones. So these are atomic numbers less than 58. And also, in this case, the nucleus releases a lot of energy when these 2 nuclei combine together here. Some of the byproducts, though, in this case are gamma rays, positrons, neutrinos. Now, this is also the first principle, though, behind the first hydrogen bomb, also known as a fusion bomb, and it's essentially an uncontrolled thermonuclear fusion reaction. Now, let's take a look here at an example of this. So we have helium and helium combining, and as a result we get an alpha particle, a hydrogen, and a hydrogen particle. So we have here our two smaller nuclei combining into a larger nuclei, and these are our byproducts. Next, let's take a look at fusion reactors. First, there's a real great desire to harness the power of, or the energy created by a fusion reaction, but the device for this purpose still hasn't been created. An example of a fusion reactor really is the sun. The sun is a fusion reactor that continues to produce energy. And its primary fuel source for fusion would be water. So, for example, a gallon, like a simple gallon of seawater, could produce the same amount of energy as 300 gallons of gasoline, if controlled. 300 gallons. So, if you fill up your gas tank with, like, I don't know, say 13 gallons of gasoline, right? Now, instead of 13 gallons of gasoline, you fill it up with 13 gallons of water. If it could run on that, you would get 300 more times that distance. 300 more times. So instead of your car running, say, on a full gas tank of like 13 or 14 gallons, or maybe 15 gallons, say it runs like 400 miles. Instead of 400 miles, you're talking about 120,000 miles. Okay, 400 times 300.